Well, welcome. I'd like to begin by talking about this fabulous opportunity we have to return to the moon. Uh, why is going to the moon so important? And what is the transformational science and exploration that we still need to do is really all about today's discussion and indeed interaction with our science community that are here. I'd really like to kick this off by asking members of our NASA Survey Institute, this is our Solar System Exploration Research Virtual Institute, to come and talk about some of this transformational science. And at the end of this particular panel, we'll bring a new panel up that will talk about how we will in the future be able to start this process of going back to the moon, not only with scientific instruments, but also in support of human exploration. So I believe this is going to be an exciting hour. The moon is a spectacular body that's very close to us, that has many hidden secrets, and I think you'll really begin to appreciate how important it is to return to the moon and do the science that we're going to talk about today. The moderator of the science panel today is the very distinguished Jim Head. Now, Jim's first job at NASA was participating in the site selection for the Apollo missions on the moon, and his participation in astronaut training soon after. Jim is a professor at Brown University in the Planetary Geosciences Department. So let me turn it over to Jim Head to moderate the panel on transformational science at the moon. Jim?
Thank you, Jim. Thank you very much, Jim. These are indeed really exciting times, and it's been wonderful for me to see my life flash before my eyes and now your eyes as to see what's happened in the intervening period. We're here today to share with you some of the new and exciting opportunities for transformational lunar science in the coming years. What is transformative science? Typically, as scientists on a day-to-day basis, we all do kind of incremental science, not negatively, but we're shaping individual blocks and building a solid foundation of knowledge and fitting the blocks into a paradigm, a framework, for our understanding, or something like a theory. We scientists call this framework a theory, a model, possibly a paradigm. Transformational science is not incremental, but instead radically changes the field of science. It destroys old scientific paradigms and creates new scientific theories and indeed models. In the language of NASA, that means a major mid-course correction. You're not just keeping going with little updates, but you're doing a major mid-course correction. Several well-known examples of transformational discoveries and theories are Darwin's theory of evolution, global plate tectonics and how the Earth works, the theory of the moon formed from a giant impact early in its history, the lunar magma ocean hypothesis, where the outer part of the moon was in fact an ocean of molten rock, and indeed the discovery of water in lunar samples. We're here today to describe some exciting opportunities for transformational science in the coming years, and we're happy that we're here today because transformational science is not done in a vacuum. In the complex world of space science and exploration, transformative science requires partnerships and synergism. It requires scientists, engineers, operations people, and all of these to work together, shoulder to shoulder in what Apollo 15 Commander David Scott, a participant in our report, what Dave calls science and engineering synergism. This is what we had in Apollo, indeed. And indeed, how did we get to where we are today? We're standing on a fundamental foundation of NASA exploration that sets the stage for the next level of transformative scientific discoveries. You all are the enablers, indeed, of transformative lunar science. This is very well shown, in fact, by these images here, where we first got an idea of what transformative perspectives would be when we saw the Earth from the moon, starting with Apollo 8 and working through the blue marble and indeed the Earth from the lunar far side of Galileo, actually coming back into the solar system where we live, that is the Earth-Moon system, and viewing it from afar. Now, one of the key things here is that this was, in fact, a good example of the beginning of robotic human exploration of the moon, human-robotic partnerships. Most people don't know that we actually launched 21 robotic missions to the moon before Neil Armstrong set foot on the moon. This was for preparation. It was excellent data. It allowed us to choose the landing sites, plan the traverses, and help the astronauts understand, in fact, what the best sampling areas would be and strategies would be. This is amazing. This is the beginning. 21 missions. And indeed, the Apollo Lunar Exploration Program scientific expeditions of the moon began with Apollo 11 in the upper left, deploying instruments, collecting samples, and evolved with science and engineering synergism all the way through to Apollo 15, 16, and 17, in which we drove across the surface of the moon multiple tens of kilometers and collected many kilograms of rocks that were very well documented by incredible scientists, leading up at Apollo 17 to an astronaut geologist going to the moon, Harrison Schmitt. I should point out that the Apollo 15 mission with Commander Dave Scott, Dave was a test pilot, very well trained. His wife, Lurton, took me aside one day and said, "Jim, you've ruined Dave. I had to go to school at night to learn geology so I could just talk to him." I considered that a badge of courage, but she was kidding, of course. But these people really knew what they were doing. And as a good example of the excitement of human exploration on the moon and what they can do, you can see on the left-hand side here the Genesis rock. Please go Google Genesis rock Apollo 15 and listen to the excitement in Dave's voice when he says, "Plagioclase, I see plagioclase. I think, Houston, we found what we came for." He knew that the bright plagioclase crystals were deep crust, and he collected that rock, and in fact, we learned an immense amount about the origin and evolution of the moon from that ancient rock. Secondly, he discovered green glass. Again, check the excitement in his voice. There's glass. It's green glass. And in fact, these were pyroclastic beads from an eruption, which in fact he collected and brought back to Houston. 40 years later, Alberto Sol in a laboratory at Brown University detected water in these and transformed the understanding of the moon in terms of its content of water and its importance in its origin and evolution. Dave also collected rocks at the edge of the rill, very excited, which we've learned a lot about the magnetism of the moon and its history of the magnetic field. And on the right, in one of the most exciting moments for me, was the so-called seatbelt basalt. Houston was telling Dave, "Get back to the lunar module, you're running low." Dave's driving back, he sees this beautiful rock perched out there that he just had to have because we'd all talked about the bubbles and what they meant about the gases in the magma. And he said, "Houston, I'm having a problem with my seatbelt." He said, oh, stop, fix that. Okay, so he takes his seatbelt off, jumps out of the rover, goes over, collects the rock, documents the rock, gets back on and says, "I think we're okay now." "Okay, get back to the lunar module." That's a seatbelt basalt. That's an explorer. That's somebody who's a scientist who knows what they want to do, and hey, that rock would not have been collected otherwise. And indeed, the 6 scientific exploration sites of the moon established the moon as a cornerstone for our understanding of other planets in the solar system, particularly the Earth-like or terrestrial planets. This is really fundamental in terms of our future understanding of the moon. It just maps way beyond our understanding elsewhere. Since the Apollo days, we've had a number of really important missions which has set the stage for a return to the moon and human exploration of the moon and further robotic sample return and other types of things that might be done from the Gateway, et cetera. We've had, in fact, the Lunar Reconnaissance Orbiter, LCROSS, detecting volatiles at the poles, and in fact, we've had LADEE studying the tenuous atmosphere and really unbelievably, the GRAIL mission, which literally puts the moon into an X-ray machine and looks at the deep structure below the surface morphology. All of these things have really set the stage for formative and transformative discoveries of the future. So finally, I'd just like to point out that we're on the verge of an incredible infrastructure opportunity here. We have the Lunar Orbiter Platform Gateway workshop that a number of us attended to talk about what we can do from the Gateway. We also have the commercial capabilities. Survey sponsored the Lunar Science for Landed Missions workshop, which was incredible, connecting with these people and talking about places to go and things to do in a commercial arena. And thirdly, we continue with the Pathway to Mars. We're dealing with landing site selection and so on. And finally, and last but not least, as an educator, we have in fact the next generation. Survey has wonderfully supported students. The 3 here you see in the lower right-hand corner, Sierra Kaufman, Erica Jawan, and Adine Denton, received their degrees on Sunday. Sierra is a Shinnecock Nation Native American, and she's studying Mars and the Moon, and Adine is also studying the planetary surfaces and Mars. And Erica Jawan got her PhD, and she will be heading to work on OSIRIS-REx here in Washington. So obviously we're setting the stage for a significant amount of transformative discoveries, And I think the key here is that you'll hear a lot about these from the next speakers, who will go into some detail about, in fact, the present, the beginning, and the record. And then we'll have a little bit of time for discussion. So let me introduce Dr. Carly Peters from Brown University, who will talk about the present. Thank you.
Okay, well, I wanted to start this discussion with this wonderful family portrait that some of you may be familiar with. This was acquired when the Galileo spacecraft came by the Earth to get a gravity assist to go on its way to Jupiter, its primary target. And as it was leaving this part of the solar system, the engineers recognized you could have an alignment between the moon and the Earth, and you can get them both in the same image. And they took this wonderful, wonderful picture. Now, for those of you who've looked at the moon many, many decades in your life, you may not recognize any features on the moon that you're familiar with. And that's because the moon is on this side of the Earth rather than the other side of the Earth. So the illuminated part that you're seeing is the far side of the moon. And the far side of the moon in full illumination looks like this. It's nothing that you've seen when you look at the moon with your eyes or with binoculars. And that dark smudge at the bottom of the moon is a very important lunar feature that we call South Pole Aitken Basin, which is the largest, oldest, and deepest basin on the moon. Very important. Of course, you can't really see that it's a basin here, but if you look at topography that has been acquired over the last 10 years, you can see this is enormous. It's the highest point in the areas that are the white areas, sort of indicating snow, but there's no snow there, down to the deepest parts in the deep purple. That's about 15 kilometers in difference in elevations. So this is an enormous basin, about the size of the continental USA. And because it's so big, it's dug deep into the interior of the moon, and it's a prime area would like to get important samples and in situ data to understand the interior of this important body. Another unexplored area, of course, is the poles of the moon. This is a more recent image obtained by the Lunar Reconnaissance Orbiter as it passed over the poles and took a beautiful image of the Earth in the process. And you can see there's very, very deep shadows here. And that small edge, for those of you up in the front, you can see it's not a sharp edge. That's because the topography in the background is in shadow, but it's cutting across the portion of the Earth image. And the deep shadows are so deep that sunlight never reaches them. They're extremely cold, and this image is from one of the experiments on the LRO that measures the temperature, and the temperature is so cold that any water or most volatiles that enter these areas never escape. So those are two areas that are completely unexplored on the moon. The present Earth-Moon system has been imaged by LRO for almost a decade now, and with repeat images of the same area have been able to identify impacts that have occurred on the surface of the moon. In other words, they have a record of the impact in this part of the solar system that we can't get from Earth, but that the moon is an excellent laboratory for doing that. And so far, they've identified about 300 and still counting. Okay, the other part of the Earth-Moon system is that space is not empty. The moon is an atmosphereless body. It does have minor particles in around it. However, there's a large amount of highly energetic particles that the sun spreads throughout the solar system. Some of which I've highlighted in blue there, hydrogen, which is the principal component that's being released from the sun on a regular basis, hydrogen, which will turn out to be a very important part of the story for the lunar water. In high school or maybe in grade school, you learned about how sodium has these very strong lines. Well, you can image the moon in these sodium lines and see that the energetic particles principally from the sun, but also from galactic, stimulate the sodium in the lunar environment. So you have this small but measurable sodium atmosphere. And of course, there's these wonderful magnetic anomalies that occur on the surface that redistribute electrons and protons and are associated with these gorgeous albedo features that have no topography, but they're most beautiful in shape and form and not understood in terms of how they're formed. Well, the rest of my short time, I'd like to focus on the water issue, and in particular, the water cycle. This is a new topic. Near the turn of the century, a very small spacecraft that was sent to the moon with a neutron spectrometer, which measures neutrons, but it found that at the poles of the moon, there was a low abundance of these neutrons. And with several analyses, they recognize that this is because the neutrons are being absorbed at the poles of the moon, and the principal absorber is hydrogen. So this was the first concrete evidence that there's probably some hydrated materials sequestered in the poles of the moon. Then in less than a decade ago, L-CROSS sent a projectile to one of these targeted areas, released materials in the process, studied what was released, and found abundant volatiles, including water, but a whole array of different volatiles. And that's from the polar areas. This image I have here, you may recognize, this is actually from the Earth. This is looking at the Kilauea volcano from Mauna Kea, which is where the telescopes are. But I like to show this because not only are there lavas being extruded as we speak, but there's gases as well. And that's an important part of magmatism. On the moon, we have extensive lavas. In fact, the lavas are all these dark features that you see when you look at the moon, either with your eye or with a pair of binoculars. These are extensive basalts that were extruded on the surface a few billion years ago. But similarly, because of the magnitude of these extrusions, gases were released at the same time. And these gases recently have been calculated to form a temporary atmosphere on the moon that's on the order of the magnitude of atmosphere at current Mars. Well, that dissipated and probably or may be sequestered in some of our polar areas. And of course, as Jim mentioned, we have lunar samples. We have samples that can be studied in the laboratory with modern equipment that continues to improve. And these glasses we've shown we've been able, with modern equipment, to detect the abundance of water and compare it with other solar system bodies. Not only that, you can identify the isotopes of water and compare that to understand the origin of the water in the Earth-Moon system. And as you'll see from the next couple of speakers, this important link between the Earth and the Moon, especially in terms of water, is critical. And of course, the last part is a topic that Jim Green and I were here less than 9 years ago talking about the unexpected discovery of hydrated materials on the surface of the moon. Not a lot, but essentially everywhere on the moon, that during the heat of the day is gone, and in the cool of the day is retained. This hydrated material, we now understand, is due to the solar wind hydrogen combined with the oxygen that's in the rocks throughout the surface of the moon. And that's why it's so pervasive. And there's hints that it's cyclical. As the night-day occurs, the hydration varies. So we clearly have a water cycle between the polar areas, the interior, the surface, and how these are all related and what aspects of solar system water they're measuring. And this, if you haven't picked up on this understanding of hydration on the moon is recent within the last decade. So there's a number of key issues that we want to explore in the years ahead. We want to identify the origin of this water at 1 AU. the lunar and the terrestrial water are both part of the same question. We want to document the mobility of volatiles on airless body, which the moon is a unique laboratory that enables us to do that. And we want to measure the magnitude of hydrated materials associated with the surface to be able to recognize to what extent these are resources and are any of them renewable resources. So with that, I give you a quick look at the present moon, and I will transfer the podium to my colleague Robin Knapp to talk about the beginnings.
Thank you. Well, there are many fascinating moons in our solar system, but among them, our moon holds a special place because of its really unique ability to tell us about the origin of our own planet. We know from the Apollo samples that the moon is a primordial ancient object and that it formed only 60 to 100 million years after the very beginning of our solar system. So it dates back to the time when the planets themselves were forming. Our models for the formation of the inner planets, Mercury, Venus, Earth, and Mars, suggest that initially in the inner solar system was a distribution of perhaps tens to hundreds of mini-planets. And as these planets gravitationally perturbed each other into crossing orbits, there were giant collisions and mergers between them, and these events decreased the number of planets until we were finally left with our current 4 planets. Now, it's thought that our Earth-Moon system was the product of one of these giant collisions. The giant impact theory dates back to the Apollo era, but it took about 20 years for us to develop the kind of accurate numerical computer simulations to simulate what happens when two planets collide. And the goal of these types of simulations is to try to identify the properties of the impact that would produce the Earth-Moon system, the mass of the impacting planet, its speed, its angle, and in turn, to use those needed properties as a key constraint for our models of how Earth-like planets formed in our solar system and in exoplanetary systems as well. So this is a 3D animation of one type of potential moon-forming impact. So the object in the upper right is a roughly Mars-size impacting planet. The object on the lower left is the proto-Earth. Here, color is going to scale with temperature. So green is roughly molten rock, and red particles are fully vaporized rock. The collision is oblique, and it's large enough that it distorts the very shape of the Earth. You'll see here there's a secondary impact of what is essentially the iron core of the impactor. In these oblique collisions, you typically form an orbiting disk with part of the debris that is in the equatorial plane of the planet. And it's from this orbiting disk of debris that we think the moon then later accreted. So in this type of collision, involving a roughly Mars-sized impactor, we knew that we could get the right masses of the Earth and Moon, the right initial spin rate for the Earth, and match the very low iron content of the Moon. And so we thought this, with very high certainty, was how the Moon formed. But in the last 10 years, that has greatly changed, and now there is tremendous debate about the nature of the type of event that could produce our system. And this all relates to trying to explain the amazing compositional similarity between the current Earth and Moon. So these impact simulations, we know from them that the vast majority of giant impacts produce a disk that comes overwhelmingly from the impacting planet, rather than from the target proto-Earth. And that's a general result. A very diagnostic way to look at planet composition is to look at the ratios of isotopes of a given element in a planetary material. So the plot on the right is showing the oxygen system. So most oxygen atoms are O16. They have 8 neutrons, 8 protons. But some have an extra neutron, and those are O17 atoms, and some have 2 extra neutrons, O18. So if you compare 2 samples from the Earth of ocean water and maybe from a cloud, they'll have slight differences in the ratios of these isotopes of O17 to O16 and O18 to O16. And this is because processes like evaporation and condensation will change those ratios. But they change the ratios in a way that is proportional to the mass of the isotopes, which we can predict. What that means is if you take any sample from the Earth, it'll fall at a different place on this curve, but it will all lie along a single line on a plot like this. Now, we have meteorites from Mars, and they have a completely separate line that we think represents a completely distinct initial reservoir of material. Okay, now, we don't, of course, know what the composition of that impacting planet was because it's gone. But if that impacting planet was as different compositionally from the Earth as Mars is today, and if we formed the Moon primarily from material that came from it, then we would expect the Moon and the Earth to look slightly different. And yet, we don't. If you plot the Moon's oxygen composition on this plot, it falls right on the Earth line. Now, we knew about this ever since we had the Apollo samples, but the precision of the measurement still allowed for some difference between the Earth and Moon. But over time, these measurements have become more and more precise, and with it, the difference between the Earth and the Moon has just gotten smaller and smaller. So the big question is, how do you take these two separately formed planets, merge them together, and yet end up with an Earth and Moon that have apparently identical initial compositions? So in the last 10 years, there have been a wide array of potential solutions to this problem. I'll show just a couple here, but there are more. One idea is that after the impact, there may have been mixing between the vapor component of this pre-lunar disk and the Earth that equated the compositions before the Moon formed. That could allow a collision like the one I showed you before to perhaps be viable. Or alternatively, people have considered entirely different types of impacts. These are thought to be very unusual impacts, but they're capable of producing a disk and a planet with the same composition. Now, we really want to be able to distinguish among these scenarios because they have very different implications for the final stages of planet formation and for the conditions under which the Moon formed. And one of the key things we need is more data that can be provided, hopefully, by future lunar exploration. And I'm going to highlight 3 areas that I think would be particularly helpful for resolving these origin questions. The first is a better understanding of the Moon's interior composition. Most of our samples are telling us about the outermost layer of the Moon, but we want to know more about the interior bulk composition of the Moon. Is it homogeneous? Or is it heterogeneous? Is there a compositional element of the Moon that we're currently unaware of? We lack in our current samples any sample of the deeper lunar mantle, but it's possible that we could get at that by exploring the South Pole Aitken Basin because that impact may have gone deep enough to excavate some mantle material. Alternatively, you've heard about the amazing science that can be done by looking at these glass beads that are produced during volcanic outflows that essentially freeze in the composition of their parent magma that originated at many hundreds of kilometers of depth. And we would love to have a much extended collection of these samples. Second key question, what was the Moon's initial thermal state? The various models for the origin of the Moon predict very different initial states for the Moon. Some imply that the Moon was initially fully molten. Others imply that the inner portions of the Moon were solid with a magma ocean on top. In order to make progress on this topic, we really need a network of sensors on the lunar surface of seismometers and heat probes. And finally, and perhaps most broadly, we want to know if when we look at the composition of Mars, is that really indicative of the composition of the large protoplanets that the Earth accreted at the end of its growth? Or was Mars different? Is Mars' composition very different from what was colliding with the Earth? This depends on the degree to which material in the inner solar system was being radially mixed as the inner planets formed. So if the inner planets formed in a relatively quiescent environment on circular concentric orbits, then it's possible that the reservoir from which Mars formed was very different than the reservoir from which Earth formed. At the other extreme, if there was a lot of radial mixing, you would expect that a Mars-like difference in composition from the Earth might have been typical of the giant impactor that produced our Moon. The degree of radial mixing in the inner solar system, in turn, depends on what the giant outer planets were doing as the planets formed. We know now from looking at the orbit of Pluto and the Kuiper Belt objects that the outer planets, Saturn, Uranus, and Neptune, had their orbits expand soon after they formed. We call that outward planet migration. And this orbital migration is due to, or was due to, the interaction of the planets with a disk, shown in green here, of small outer planetesimals in our solar system. Interestingly, as the orbits of the planets expand due to these interactions, at one point Jupiter and Saturn pass a critical distance. And as they pass that distance, there's a dynamical instability in the system that you'll see very clearly in this animation. And when that instability takes place, it showers objects, cometary objects and asteroids into the inner solar system. So here is a simulation. Those are the initial giant planet orbits. So the terrestrial planets and Earth are forming down in the center. And after about 900 million years, they'll pass this instability point and acquire their final orbits. Now, in this case, the instability happens about 900 million years into solar system history, long after the terrestrial planets are done forming. And when it happens, it would have produced a spike of large impactors in the inner solar system. And so if there was a late instability, we should be able to go and date the large basins on the moon, and we should see a concentration of ages of those basins around the time of this instability. Now, while it's generally accepted that the outer planets migrated in this way, what's a matter of great debate right now is when that migration happened. If you change the assumed conditions of that planetesimal disk, you can have the migration happen much earlier as the terrestrial planets are forming. And this animation is showing you a simulation of that early type of instability. If the instability occurs as the planets are forming, it drives a lot of mixing in the inner planet region and sends a lot of material from Mars's region into the Earth. And in this case, we would expect that you would see a lot of compositional diversity between a moon-forming impactor and the Earth. Now, in terms of the bombardment rate, in this case, we would expect that we should see extremely ancient basins, and that the impact flux as recorded by the moon should just decay relatively steadily with time. And so this is critical, and I've emphasized the relationship here to understanding the origin of our Earth and Moon because it affects the radial mixing in the inner solar system. But determining whether or not there was this early versus late instability is also very important for constraining the properties of the disk from which our planet formed. So with that, I will turn it over to my colleague, Dave Kring. Thank you.
Good morning. So I hope you understand that we're really excited about the opportunity to go back to the moon, explore our neighbor, and learn more about the rest of the solar system. A large part of what you've been hearing this morning and what we hope to learn in the future will rotate around our ability to collect samples, okay? The Apollo sample collection has been incredibly invaluable in shaping what we now know of our solar system. And I'm going to illustrate that with a few big ideas that have emerged from those analyses. And I want to actually put it in the context of publications that reflect the importance of those samples. So you'll notice here that I'm referring to the journal Science. This is one of the United States' most prestigious science journals. It is the place where you put transformational scientific discoveries. And thus far, 124 papers with Apollo sample analyses have been published in that journal. That in itself is a huge result. Okay, so one of the takeaways is lunar samples returned to Earth have generated an enormous wealth of transformational scientific knowledge. Here are 4 examples. You've heard a little bit about some of these. There is the idea of how the Earth and Moon formed in a giant impact. As Robin indicated, that idea began to emerge with chemical analyses of lunar samples. It's been complemented beautifully by some of the dynamical calculations that she illustrated. And in the end, to really solve this problem, we need to go back to the moon and collect very carefully some selected samples. There's the lunar magma ocean hypothesis, which you've already heard about. The moon is, in fact, a differentiated world. That was, in fact, a huge outcome of the Apollo 11 mission. A Nobel laureate, Urey, who had discovered deuterium, said the moon is one big chondrite. Well, it took Neil Armstrong and Buzz Aldrin a few minutes to demonstrate that that was not, in fact, the case. There is the concept of this lunar cataclysm. That is, several hundred million years after the Earth and the moon formed, there was a flurry of asteroids and comets that struck the planetary bodies in the inner solar system. So the tagline there would be wandering worlds, resurface worlds. And then there is the impact origin of life hypothesis. It has been postulated that that bombardment in the Earth-Moon system, in fact, may be tied to the origin of life on our planet and potentially elsewhere in our solar system. And more recently, there are two emerging hypotheses. There is something called the lunar magmatic epoch hypothesis, that immense SPA impact basin that was described earlier. That impact event may have caused a spike in the magmatic activity on the near side. And then there, of course, is this issue of the origin of lunar and Earth water that you heard so beautifully described a few minutes ago. Okay, I'm going to try to expand on the details of that period of bombardment. And so what I've plotted here is the flux of impacting asteroids and or comets on the vertical axis as a function of solar system time from 4.5 billion years ago to today. And immediately after the moon-forming impact, of course, the impact rate would have been quite high, as you see illustrated in that graph. Based on the Apollo sample analyses, we do have this notion that there was a spike in the collisional activity that occurred about 3.9 billion years ago. That is, in fact, what we call the lunar cataclysm. That said, we only went to a small number of sites in a limited region of the moon, and so there is still a lot of mystery as to what happened between 4.5 and that 3.9 billion year set of events. And you'll see that I have illustrated that with 4 different curves. We at this moment don't know which of those curves is correct. And really the best way to resolve that issue is to go to some selected basins like the Schrödinger Basin, the Orientale Basin, the SPA Basin to put some hard constraints on that curve. Now the astrobiologists, of course, are interested in this because there seems to be this coincidence in time between the ending of the basin-forming epoch on the moon and the emergence of life on our planet. And so there is some question as to whether, one, there's a cause and an effect associated with that. The punchline here is the moon is the best and most accessible place in the entire solar system to evaluate this early solar system bombardment because geologic processes have largely erased that record elsewhere. Okay. Putting this all together, our good friends at the Goddard Space Flight Center put together this movie that captures that early molten moon, and we'll illustrate in just a moment the giant SPA impact event followed by that period of bombardment. You'll see some notional times put on these processes in the upper right corner. Some of those times come from our own group's work, but I have to say they're notional, and those are the types of numbers that we definitely want to test with new samples from the moon. Okay, when that was occurring, the moon was much closer to the Earth than it is today. So in the chart in the upper left, you'll see the Earth-Moon distance as it exists today, about 60 Earth radii. Soon after the giant impact occurred, the moon was very close to the Earth and about 16 times bigger in the sky. Imagine a big glowing orb of molten lava hanging up in the sky. It had moved a little bit farther away by the time the bombardment was occurring, but the point here is whatever was occurring on the moon was in fact occurring on the Earth. In fact, dramatically more so. So we currently estimate 200 impact basins, 1,000 kilometers in size, and 4 to 5 impact basins greater than 5,000 kilometers in size were produced on the Earth. This collisional evolution would have eroded Earth's primitive atmosphere. It would have episodically vaporized its nascent seas and likely affected the origin and early evolution of life, as I postulated earlier. And so this begs the question, could life have in fact emerged from an impact crater on Earth and potentially Mars? Okay, the moon is also an absolutely critical element in setting the solar system's clock. What do I mean by that? Well, as a planetary surface ages, it has a greater opportunity to be hit by asteroids and comets, and so the crater density increases, and we've been able to calibrate that on the moon in a very few number of places. But it is important to go back to the moon, select samples so that we can refine that calibration, and then we will be able to identify the ages of cratered planetary surfaces throughout the solar system, regardless of where they are. And then, of course, we have the the evolution of magmatic worlds, of which the moon is a great example. You've already heard about the magma ocean hypothesis, and that begs several questions here that we're excited to answer. How long was the magma ocean molten? How fast does a planetary crust form? Do mantles overturn? How long does a core dynamo operate? How long does surface volcanism persist? And how does that volcanism affect planetary environments? As you heard earlier, that volcanism on the moon, in fact, may have created temporarily a transient atmosphere around the moon. And each of these questions that I've just identified can be addressed with suitable samples from suitable landing sites on the moon. Okay, so here's that slide that I showed earlier, and now I want to add a bullet that to produce transformative science in the future, we need additional samples from other lunar surface sites whose locations are guided by those past Apollo missions and by the spectacular orbiting data that's been collected in the past. And there's no really uncertainty as to where to go. We've studied this now for 45 years. Here I showed just one report with outlined some of the landing site opportunities on the moon, and I want to take just a moment to illustrate the types of things that we can learn from one of those landing sites that's been identified in those previous reports. I'm pointing you here to the Schrödinger Basin, which is within the South Pole Aitken Basin, the SPA Basin on the lunar far side. If you were to select or collect rocks from that uplifted peak ring, you can test the lunar magma ocean hypothesis, test the giant impact hypothesis, and tap into lunar water cycle. If you collect some of the marite or basaltic lava flows and the pyroclastic vents that occur in the center of the basin, you can address the thermal and magmatic evolution of the moon, and again, tap into the lunar volatile cycle. Perhaps most excitingly, if you go to other parts of the basins, you can collect both samples of the Schrödinger impact event and the SPA impact event and determine the duration of that basin-forming epoch on the lunar surface. And all of these objectives are high-priority science objectives that have been identified by the NRC for NASA in the past. There is also rich ISRU potentials at this landing site too, and so here is a close-up view of that pyroclastic vent that I mentioned a moment ago. This is probably the largest indigenous source of water in the South Polar region of the moon. This type of vent could be responsible for a large fraction of the water ice that we hope to recover in the future. In addition, the pyroclastic glass can be excavated and transported and processed as building materials, the iron and titanium in the Mare basalts can actually be reduced to produce water. Okay, we have, just briefly want to point out, have detailed landing sites and traverse studies, so we know exactly how to collect these samples. In fact, we've already identified specific rocks we would like to be collected. And so let me close with just 5 short bullets. I suggest that we explore the unexplored and go to the lunar far side and poles. I think that leadership begins with meaningful missions, which means we should land on the lunar surface. To make truly transformative scientific discoveries, we need sample return missions to high-priority landing sites, an integrated robotic and human exploration program with international and commercial partners will produce the greatest science, and I urge all of us to remember it's critically important that we engage the public and Congress. We need to provide certain assets like communication relay satellites so that we can get the right type of data onto people's televisions. Thank you.
Thank you very much, David. Jim, why don't we combine the questions at the end? Is it okay? So, you know, in our survey-sponsored work at Brown, we get together with the engineers, the planetary geoscientists, and the engineering students who are designing spacecraft and mission operations and things like this from the get-go, shoulder to shoulder from the beginning. And what we tell them is, gee, can you help us as engineers make our scientific dreams a reality? And so now I'd like to turn it over to Jim Green, who will introduce the people that are going to make our scientific dreams a reality. And I'll ask the panel to.
Thank you very much. Well, this has been a really exciting science panel, and I have now we're going to move into the second phase of our discussion, and that is how are we going to be able to accomplish some of the fantastic opportunities that were talked about in returning to the moon. I will point out that Survey has put together a nice little overview of the transformative lunar science activities that those here present today can pick one up in the back of the room. Now I'd like to introduce our panel. The second segment will indeed dwell upon the execution of our program that we've put together in terms of returning to the moon. And to discuss that exploration strategy. David Scher is the Deputy Director of the Planetary Science Division, and then with him is Jason Cruson, who's the Director of the Advanced Exploration Systems Division, and we'll start with David.
We're pulling up the charts. What we want to do is walk through fairly quickly, because we're running out of time, the new programs that we've got that will be. So what we want to do is walk through the new programs that we have that are focused on our return to the moon. There we go. So this is a chart that we've built that shows the integrated NASA exploration campaign. It's a mix of activities that are being conducted out of the Science Mission Directorate, the Human Exploration Operations Mission Directorate, as well as STMD. So starting from the top, which is really the activities that are ongoing now, recognizing the work that was done on the Apollo program and a lot of the work that is done, and as was just shown to you, all the papers that are a result of all the analysis that's been done on the samples that were brought back from Apollo. We're investing today in trying to make all of that data, that analytical data on the samples, the analysis that's been done over the last 50 years available, more easily available. So we're investing in actually creating digital archives where a lot of that data today exists in an analog form. So as we look forward, picking up from these new programs, we can take advantage of the science that's already been done. We currently are working on CubeSats that are going to the moon. They're orbital. Several of them will be flying on Exploration Mission 1. And we just released our announcement of opportunity for Simplex 2, which is also encouraging lunar CubeSats. So the program that we've got today is already working on pieces of going to the moon, and then with the President's 2019 budget, which came out in February, we rolled out a whole new program. It's the Lunar Discovery and Exploration Program. Its focus is on taking advantage of this developing commercial industry that's interested in going to the moon and buying services from commercial landers. So the science focus over the next 4 or 5 years will be to develop a pipeline of payloads and contract with industry to find opportunities to fly those payloads to the surface of the moon. The idea is that commercial industry has a business case for doing this. It's not just for NASA, so we're the marginal customer. We will go with them where they want to go. In some cases, we might tell them, here's a great place to go. They've been involved in a lot of the workshops that we've been doing about those places that are scientifically interesting on the moon. So they're paying attention to where the scientists want to go, and I think will probably align themselves with some of the best ideas that are coming out of our science. But over the next 4 to 5 years, we'll be focusing on Taking advantage of those, early missions will be simple landers, if you can call landing on the moon simple, that will likely last just a lunar day. These are not companies that have figured out how to survive the lunar night, the 2 weeks of darkness and the cold temperatures that you got. Probably start off in the mid-latitudes, but ultimately we want to see them get down to the poles where we can do some really interesting work searching for volatiles, get to the far side once we can provide communication relays, and if we can develop the capability to survive more than just a 2-week period on the surface of the moon. Our expectation is that if there's a robust capability that industry is interested in, the commercial industry is interested in, ultimately they will even develop capabilities to bring samples back, to do some amount of mobility on the surface of the small rovers or other mechanisms to move around that will provide more opportunities for us to conduct science. And that kind of feeds into the next half where our HEO friends talk.
Yeah, so in addition to those near-term opportunities of commercial launch vehicles and commercial landings, and all the great science instrument development that the science side is working on, we also want to start increasing our lander capabilities from kind of those simple initial landers to medium and large landers, actually leading to a human-capable lander. So the next set of activities is we intend to do 500 kilogram class initial demonstrations of human lander capabilities, so leading towards that. First of those missions in 2022, second one in 2024, and then hopefully a natural progression after that, leading all the way to human class lander capabilities. So on this chart, you see kind of 500 all the way up to 5,000 to 6,000 kilograms class. That's kind of the progression that we'd like to see in this time frame. In addition to that, another key piece of infrastructure is the gateway. The gateway, and actually I'll have a separate slide on that to give you a little bit of an overview of that. So you can think about this as a lunar outpost in orbit around the moon. It's an optimized orbit to minimize propellant usage, so our maintenance costs are lower to keep it there. It has things like a power and propulsion element, so it can move around and change orbits if need be to conduct different scientific aspects or human spaceflight missions. It has the ability to support humans, so habitation and utilization capabilities that we're familiar with utilizing today, probably more than one habitat, but it'll be human-tended, so a crew of 4 for 30, 60, 90-day kind of missions on a periodic basis. We'll be able to do logistics flights and robotics for installation of instruments on the outside of it, and eventually we'll have an airlock capability to do EVA assistance for either science and or maintenance as well. The very first of those elements is that power propulsion element. You can think about this as a very highly capable geocommunications satellite in orbit around the moon. This will be there by 2022 and start assisting the science missions right from the very beginning. And then that whole payload suite will be available out there for payloads of all types, whether it's lunar science, as we're talking about today, or heliophysics, astrophysics, and even biology type experiments as well. So it's a kind of a unique environment for a lot of that science, and we're really excited to get the development of the gateway underway.
And to kind of tie these all together, I think it was David who was talking about the desire to get additional samples from the surface of the moon with lunar capabilities provided by the commercial industry. They don't have to solve the entire return problem. Once the gateway's in place, we can look at architectures that allow us to get samples off the surface of the moon and into orbit, and from there, possibly to the gateway. And then there's regular return trips, since the astronauts also come home. They don't just go on a one-way trip, which will allow us to close the loop on getting samples back to Earth.
Yeah, thanks.
All right, very good. So I'll share the microphone here with you, David. So this is a really exciting time. As we heard, we've got a lot of science yet to do on the moon. And then, of course, with the opportunities that the commercial sector will provide to us, and supplemented with the gateway, which will be really transformative in our ability to get to the far side of the moon because of the communication capability and the way the gateway can provide us access for return samples to go to. So let me start out with some of the questions that many people I'm sure may have on their mind. And that is, how are you, Jason, gathering information from the science community in involving them in the design of the gateway?
Yeah, so it was referenced earlier. We ran a very, I think, successful science engagement workshop earlier this year in Denver. We had over 300 abstracts, 180 presentations, 75% of those are all from scientists from the community in heliophysics, astrophysics, earth science, planetary science, of course, and then our biology and life sciences communities as well. So what we're doing there is at the very beginning engaging with the science community to make sure that we're building a gateway that has the functions to enable the science activities. So this is at the very front end. And already from that, we've modified the ways we want to do use of our logistics vehicles. One of the ideas that was brought up for our planetary science is maybe there's a need to go to a low lunar orbit. So why not use our logistics vehicles once they come and go from the gateway, drop down to a low lunar orbit, conduct a series of a science campaign, move back up to the gateway, remove instruments, and then the next logistics vehicle could actually conduct the same mission again if it wanted to. So things and ideas like that have come out of the science community, and we're already listening to that and factoring into the way we're going to build the gateway.
Yeah, that sounds excellent. That really provides a lot of flexibility. Yeah. You know, well, we've been talking about potentially strategic knowledge gaps, those things that we need to know before we go back to the moon, particularly for humans down to the surface. Do you think we still have a number of things and a number of strategic knowledge gaps that we need to close before that happens, or are we well on the way?
So I think there's actually an incredible amount of data we still would love to have. It will definitely be enhancing. And then some things that are really critical, if we think about human spaceflight architectures, understanding of the volatiles, entrapment of water and those types of the entire water cycle, Carly was pulling on the renewability of that water cycle, that would have a drastic impact on our human spaceflight architecture and the amount of logistics chain that we need for it. So that volatiles is kind of probably highest on my list of measurements, in addition to all the environmental factors where we're sending the crews.
Okay. I think at this point, let me ask Jim Head to come up and join our panel, and then we'll open it up for any questions that people here in the audience may have. You have some science questions, or please come to the microphone, or talk about exploration strategy. The experts are here.
Hi, I'm Jen Helman from NASA.
You may have to turn on the mic, Jen.
It says on. It's green.
Yeah,
Okay.
there it goes.
Hi, I'm Jen Helden from NASA Ames, and it's really inspiring to see all of you on the stage and to see the human exploration side talking with the science mission directorate. And so I guess I have two questions related to that, because I think that that's one of the greatest aspects of our agency, is that we do have the opportunity to merge science and exploration. And that's why I'm here and why I think a lot of us are here. And so I'm wondering, as we go forward with the lunar campaigns, is there a formalized process within NASA for identifying what the strategic knowledge gaps are and how those map into the transformative lunar science measurements that are needed? Because I think I would argue that there's a lot of overlap between the measurements that are needed for HEO and SMD. So I'm wondering how we're planning to identify those to prioritize the measurements and missions. And then my second question is, once we've done that or identified what NASA needs to do or needs to know, is there a mechanism to feed those needs into the commercial sector for the capabilities of those mission architectures and profiles? Or do we just go the other way and say, this is what they can do, and then we fit our NASA needs into that?
Let's start with the first part.
Yeah, what'd you take?
So, yes, strategic knowledge gap. So these have been we keep on updating them. One of the updates for the lunar strategic knowledge gaps was actually here recently. And actually kind of mapping strategic knowledge gaps to the scientific opportunities that are out there is an ongoing activity that we engage with the Lunar Exploration Analysis Group and many in the science community as well. So that's an active topic. You do want to find that the maximize the overlap of exploration measurements with science measurements. A lot of our measurements on the human spaceflight side, we don't need the scientific precision in a lot of cases. It's existence proof is what I say sometimes. So our precision is not anywhere near what's needed for science cases. So we fit very complementary in the science measurements. Scientists tend to like to get a lot more precision on those measurements than we would. So we encourage that. But yeah, there's a lot of collaboration with that. And actually the recent solicitations that the Science Mission Director is putting out, putting strategic knowledge gaps and the scientific decadal measurements on kind of equal footing in a lot of those calls, I think is a representation of that desire of NASA to actually balance the two.
Yeah, I would just add to that, I think it's really important, Jen, that to see this group here today. And, you know, in Apollo, the science and engineering synergism was absolutely amazing, literally shoulder to shoulder. That's why we got the capabilities we did. They turned our dreams into reality, literally on Apollo by J missions in Apollo 15, 16, 17. And indeed, this is where Survey comes in, I think. You know, we really have the capability and have we're practicing this science and engineering synergism, HEOMD, SMD, working together on this, and we really look forward to continuing that in the future. Now we have a great opportunity. I think you're looking at a science and engineering sandwich here of some kind of group, and it's great. I think it's really the way to go in the future. I'll leave your mind to imagine what that actually, if it's a BLT or whatever, okay? But.
And for the most part, when we talk about the strategic knowledge gaps, the data that is needed to answer those questions are developed through the same types of instruments that we've been using for planetary science for decades. So it's not like we're having to create something completely new to answer their questions. They're really subsets of what science questions we've been addressing in all of the planets. So when we get to the moon with a specific set of instruments, it may be more precise. It may answer more than just what the SKG is interested in, but the overlap is going to be very good. The second question was asked, are we taking what we're getting, or are we going to try to drive to particular locations? If commercial industry can get to the moon, we'll go with them. I expect that if they start this out, it's going to be difficult. It's risky. U.S. hasn't gone to the moon in 46 years, so it's not like there's a wealth of experience lately. We'll go wherever they want to go. They know the areas that are of great interest to us, and I think as they build up capabilities over time and they build up experience, we'll try to help guide them to the places that may be more scientifically valuable or from an SKG perspective more valuable. But to start off, we're going to be happy being able to get to the surface of the moon with new instrumentation for the first time in quite a long time.
I think just one last point on that is that the Landed Science Workshop that Survey sponsored recently there were 8 commercial entities that came there, and it was like a bonding experience you've never seen. So they were really looking for places where they could optimize things. So I think there's a lot of good discussion that's already started.
They're paying attention to what our desires are because they're looking for as broad a customer base as possible.
Gary Jedlovic, Chief Scientist at Marshall Space Flight Center. Kind of a follow-up to that discussion there. How do you envision science PIs engaging commercial landing services to maximize the scientific return?
Maybe I haven't thought through that specific aspect of the question. Right now, the way we're approaching this today is we've got an RFP out for commercial lander services. So that's ongoing right now. The draft's out. The final will come out in July. That's to get us engaged, to get on contract a certain number of the commercial entities who are going to be trying to go do this. At the same time, we're in the process of drafting announcements for procuring instruments that can go fly on those landers. The expectation is that we will be relying on the commercial entity to lead their missions. We're going to provide a payload. We'll engage with them on, come up with a task order that says, here's the thing that we would like to fly. Here are the interfaces we need, the team that's going to work it. But we're going to try to let the commercial entity drive as much as possible to meet our requirements. A lot of this is going to get worked out better after we select these entities and can start having some conversations about the best way to go work together. We're really treading some new ground in that we're trying to treat this as a pure commercial entity where we're a marginal customer. They have a lot of other customers. RPI is going to be horse trading with other customers who have an interest in going to a location. If we're the predominant customer on a given mission, we'll probably have a little bit more of a say in what we do and how we go do it. But our intent is to really rely on that commercial entity to manage this for us.
Okay, last question since we're running out of time.
Hopefully this is a fun one. I'm Mark Kushner from Goddard Space Flight Center. Is anyone thinking these days about a space elevator to the moon?
I'm sure the answer to that's yes, but we're not currently working in that in the projects we got in front of us.
All right, with that, I'd like to thank everyone that had the opportunity to come and listen to what we're planning, great science that is in front of us that we want to execute on, and you're hearing just the beginning part of how we're going to put together the program to be able to do this science. So thank you very much.